so the next question is, can you please guide me about a beginner's guide to malware analysis? And that's a great question, because what we're going to do is we're going to transition into talking about some really cool malware. Okay, awesome. So take a 10-second break, just drink some water. Close some tabs. We're now going to talk about WindShift. And let's see, what did I want to start with first? So WindShift was really interesting because it was a new piece of Mac malware that was attributed to an advanced APT. And that's kind of cool because a lot of the new Mac malware we see is kind of not all that exciting. It's like some lame crypto miner, which like you have to like download some infected app and I don't know, run it. And then the only thing it does, it like persists, yeah, but it like just like, I don't know, mines cryptocurrency on your computer. So from like a malware analyst point of view, like that really doesn't get me that excited. However, when I get a piece of malware that's being used by an APT group that targets individuals in, governments, for example, Middle Eastern governments, that to me is like super awesome. Like that gets me excited. So I learned about WindShift from this talk at Hack in the Box. And Taha, who is the, I think, director of research at Dark Matter, presented this interesting talk called The Tales of the WindShift APT. And it was good. It was like a good overview talk. He talked about kind of how they worked, who their targets were, covered some of their Mac capabilities, but didn't really dive really deeply into the technical aspects of that. So I was super intrigued. But again, I really wanted to dig deeper into some of the techniques. So again, credit to Taha and Dark Matter. They were the ones that discovered this malware. It's kind of interesting because Dark Matter also, I think, does some other stuff, but apparently they also do malware. Now, apparently they also have a defensive mission doing malware analysis. So that was interesting to me. So in his talk, he basically mentioned that this malware was infecting Mac computers via custom URL schemes, custom URL handlers. And that was kind of interesting to me. And he gave just enough information for me to kind of figure out how this was going. Because originally the samples for the malware were not publicly available. So I couldn't just go reverse engineer. And we'll talk about how I was able to find some of them later on VirusTotal. But let's first talk about how the attackers, again, this APT group, was targeting Mac users in a kind of creative manner. So I wrote a blog about this. So if you're interested in all the technical details, you can follow along or print this out or read it after the fact. But what we're going to do is we're going to illustrate and talk through the technique these attackers use to infect Mac computers. So I'm trying to just scroll through this blog to get to the interesting point. But in Mac OS, there's this concept of URL handlers. And if you use a Mac computer, which I'm assuming most of you do, I'm sure you've come across these. A URL handler is something that basically tells the operating system, hey, I handle this type of file. And so you can say things, for example, like I handle PDF documents. That's a document handler. A URL handler is something similar, but it basically tells the operating system if someone makes a URL request locally or via a web page, and that's very important, we'll get to that, please launch my application. So this is a legitimate capability of the operating system. This is something that Shazam used, and actually something I use as well in Reiki. We'll just show this really quick. If we go back to Reiki, when the login item wants to notify the user, so we'll just, it's like Reiki : // yeah. So in the notification bar in the taskbar, again, this is the login item that's running. So this is a separate process. When you click on scan or preferences, it launches the main application. And it launches the main application to either show the current event taps or to show the preference window. So somehow I need to launch that application and tell it what window to open. More importantly, if it's already running, I have to send a message to that. So the way I do that is with these custom URLs. So for example, all I have to do is invoke the URL method, open URL, and I specify the Reiki : // URL. The operating system knows that my main application is the application that handles that. So when anybody, for example, the Reiki login item invokes this, again with this custom URL, if we come over to the main application, we can see that there's this application open URLs method that gets invoked automatically by the operating system when anybody invokes that Reiki URL. And you might be wondering, how does the operating system know to invoke my application? And that's the million-dollar application question, and that's what the attackers were exploiting. So if you go into the info.plist file, this is a property list file about your applications. In there, I've created this URL type key. Again, this is something that's fully supported by macOS. And what I say is, I will support a URL scheme called Reiki. This means, again, anytime somebody calls the Reiki : open URL, the operating system will know that my application supports that because I have in my info.plist file specified that key. So it's kind of like we're registering with the operating system. Now, there's a problem with this, which the attackers took advantage of, and we'll get to that in a second. So I think I have a VM. Let me just pause this VM and hop over to this one. Just disable this for a second. What we're going to do is we're going to copy the a proof of concept file that exploits the same vulnerability as the WindShift or the WindTail malware. And again, this is because when I first saw the talk, I didn't have access to that. So what I'm going to do is I'm going to first run a command, and then we'll show that nothing is found, and then we'll show that when I do some action, something is found, and then we'll walk through exactly what is going on behind the scenes. So I'm going to WindShift. I'm going to execute the ls register dump command. And if we run grep, we can see that there is nothing found in this, the output of this file. I'm now going to copy a file called attachments.txt to the VM. And all I've done is copy that application. I haven't actually run it or anything. But then if I run this command again, you can now see magically in this system database is all this information that basically has information about something called WindShift. And actually, let's pipe this into less so we can see more information about this. So if we look for attachment dot, cool. We can see there's a new entry in this. So what lsregister.dump is doing is it's dumping a database of all the URL handlers. And the interesting thing, and you probably picked up on this, as soon as my application hit the file system, it was automatically registered. There was no pop-up saying, hey, do you want to register this application handler? Nothing. Mac was basically like, oh, I'll do you a favor and I will just register this for you. So again, we can look now in this database and we can see my application, desktop attachment.txt, has been registered, and you can see it basically registers this canonical ID. And if we get down here, we can see information about the application. And then here's the important part. We can see that it has parsed our plist, our info.plist file, and grabbed the URL handler. And you can see that, again, if we just, oh, there's my dog again. We can, Havana, calm down. The Russians, they're always here. We can see that we've bound to this name and URL type is WindShift. If we look at the info.plist file for this, it's going to be in contents, info.plist. We can see, again, here is the keys we've specified. Again, so this is from our application bundle. This is basically saying, hey, this application handles the WindShift URL. Okay, so now here's the magic. We now come to Safari, and we open a new tab. and we type WindShift : // blah. If we do that, we get a prompt saying, do you want to allow this page to open attachment.txt? You're like, sure. We get another alert saying, hey, you're opening this for the first time. Users might click yes. But if they do that, we now have our application running from the web page. Again, we didn't actually ever launch this application. We basically just dropped it to the file system and then browsed to this URL. So here is a good overview of pictorially what happened. I think I made a nice diagram of this. And this is what the attackers basically did. So they basically got the users to visit a malicious website. So they sent them a link, an email, basically say, click this. Once the users came to this website, the website would download the zip file of the malicious malware. And what Safari does is very kindly automatically unzip archive files for you by default. And the problem is, as soon as that zip archive was unzipped, that meant the application was now on the file system. Again, it was automatically downloaded from the web page. The user hasn't done anything at this point. The OS has automatically registered that application custom URL scheme because, again, it's just trying to be helpful. The website then invokes some JavaScript to load that URL, for example, WindShift : and I think I have an example of that. Yeah, you can do something like this in JavaScript, which will just trigger a URL load. And then the operating system will automatically try to handle that URL and basically say, hey, who handles this? And then I'll say, oh, this application that was just downloaded. And then it will launch that application. Now, there's one caveat here that there are some pop-ups, as we saw. But the interesting thing is you can control the kind of contents of this pop-up based on the name of your application. So you could call your application attachment.txt. You could call it apple.com. You can even call it emojis. So for example, if the user was at a page and it popped up saying, hey, do you want this page to open apple.com? Some amount of users will click allow. It's also important to know, oh, Havana. Oh my God, she's gonna kill the camera. Come here, come here, underneath. Stay. Dogs. Okay, can we still see okay? Move a little closer. We can basically control the name of that application in that URL. And again, older versions of Safari didn't actually alert this at all. So this was kind of problematic. The web page would just automatically launch that application. So again, a lot of users, would click allow, and if they click allow, then their system will be basically infected. So again, kind of a slick technique that this APT group was using to infect systems. All right, I'm gonna look and see if there's any more questions. Hi, Patrick. If you needed to write a rootkit, how would you deploy that? Sounds like an interview question. I'm not gonna answer that right now. Maybe send me a DM on Twitter. Someone said, will you make a Mac malware VM available with Mac analysis tools? That's a great question. Right, there's some Apple licensing issues perhaps, but what I might do is create a instruction saying, look, once you have a VM, this is how I set it up. These are the tools I would install. So maybe a little blog or tutorial about that. Because again, sharing a VM, I'm not sure if that's something I am allowed to do. Okay, so WindShift's WindTail. So again, this was all based on his talk. Again, great talk, but I never actually had a copy of the actual malware, which bothered me. What I did notice was that, and let's go back here. In his talk, and let me just open this other blog. I think it's 3B. He had a slide that showed this window that basically said meeting_agenda.zip. And he talked about how the attackers were targeting users. So one of my friends said, hey, let's look for this file on VirusTotal to see if it's there. So again, kudos to Phil. Great idea. It's like, why didn't I think of that? So here we're going to hop over to VirusTotal, and we can basically do a search for anything called meetingagenda.zip. Again, we're trying to find the actual implants, the actual malware from this attack. Because again, the hack in the box talk, which was an incredible talk, didn't actually provide any of the malware samples for us to analyze. So again, when we created that exploit, that was just proof of concept code, right? That was something I basically figured out from the talk, and others did as well. But it's not something that I found from analyzing that. Do you know why you didn't get the malware? Because dark matter probably created that. Dark matter was the company that gave a talk about it, and also my understanding, without saying too much, is that dark matter provides some defensive capabilities, for example, malware detection, incident response, to Middle Eastern, probably governments, maybe companies. So the fact that they found this malware targeting those exact targets, I would doubt that it was maybe the other side of their company writing that. That would seem like, you know, bad form if the defensive side of the company is talking about malware that the offensive side wrote. But, you know, who knows? My guess is it's probably another APT group, and there's some interesting attributions that we can get into after that. But again, I wanted a copy of this implant because it was like, oh man, APT Mac OS backdoor, that's always super interesting. And it's kind of using this interesting exploit capability. How do I get that? Kaspersky. Well, who knows? So if we search for meeting_agenda.zip, we can see that there's a few hits. There's ones that don't match, and then there is one that matches the exact file name. And if we click on this, this is now detected by a lot of AV products. At the time, it wasn't detected as much, but we can see it's detected as WindTail A. So I was like, oh, sweet, this piece of malware is on VirusTotal. This is great. Like, nobody told me. And actually, a lot of the other AV people I talked to were not aware of this sample as well. So this was cool. And then the next thing I did was I said, I wonder if there's other samples for this. So the way we can do that is we can go to, again, in VirusTotal, and we can say similar, I think it's -2:, and then you put in the hash. And what this will do is this will look for files that are similar to the one that the one was just detected. And again, there's going to be some false positives. So these are some legit applications. But here you can see, let me make this a little bigger so y'all can see. Again, meeting agenda is the one that we know is malware because it matches the talk. And once we download it, it also has all the characteristics of a Mac implant. But we can see there's other files, for example, final_presentation, scandal_report, npcagenda.zip, that have a similar naming scheme that at the time were not detected or detected by very few antivirus products. So if we click on those, we can see, okay, this is also WindTail.a. So if we go back to the blog, when I originally did this, meeting agenda was only detected by 2 AV products, Kaspersky, interesting, and Zone Alarm, interesting. It's Russian and Israeli. And then when we did the similar to search modifier, we saw that there were these other ones, the NPC agenda, scandal report, and final presentation, that did not have any detections. So this is kind of cool because it means we've uncovered new variants of this malware that none of the AV products at the time were detecting. So if we download these, we can see that they are applications, but they use Microsoft Office documents, likely to avoid raising suspicions. There's a question, will the custom URL scheme work for iOS? I believe so. I think the problem is, though, you would still have to somehow get an app on the file system. So I don't think like you could from a Safari page download a rogue application and then get it to launch. Again, the custom URL schemes are designed for legitimate functionality. So I think if you have 2 applications, perhaps from the same developer, you can send messages in between. So it's kind of like an IPC mechanism. But I don't think you could, on iOS, abuse it for exploitation purposes. But that would be something I think that's probably good to look into. Other question, can you expand Reiki to work as a hardware solution? Not sure how I do that because hardware solutions are usually very, very difficult to detect in software because by definition, they are hardware-based running outside the system. So I don't think I would be able to do that, at least not in the way the application is designed. Okay, so hopping back to this malware, again, it's called WindTail, and it's being used by the WindShift APT group. We can see that if we download them, that the applications have been, sorry, the certs that sign the applications have been revoked. And if we come over here, these are the samples. Password for this is always infected with a 3. This is always on the website because I think sharing is caring. So now, be aware, if you download these samples and unzip them, macOS in the background will automatically, as I mentioned, register the notification handlers for these. So now if someone else takes you to a website and loads that custom URL scheme, these applications will get launched. Again, there'll be a pop-up asking for that, but as we showed, that pop-up is, can be slightly influenced by that. So again, this is kind of not something I don't know if this is a security risk per se, but it would be really nice if macOS asks you anytime an application registered a custom URL handler. So here's final presentation. If we click on signing information, we can see that the certificate has been revoked. Interesting. And why is this interesting? This is interesting because at the time, meeting agenda.zip, or sorry, final presentation.zip was not being detected by any antivirus products, but the certificate has been revoked. Who revokes certificates? Apple. What does this mean? It means Apple knew about at least the signing certificate used by this malware, which means they likely knew about this malware, but did not tell anybody about them. This bothers me, and I will caveat that they may not have permission to share this information. So if that's the case, I apologize to Apple for kind of giving them a hard time. Maybe, again, and this is all hypothetical, maybe dark matter who detected the malware went to Apple and say, hey, heads up about this, please revoke these certs, but don't tell anybody about that. But knowing Apple, it's possible that they discovered this malware, revoked the certificates, and then decided not to share any of this information with the antivirus community. And to me, this is a little problematic. A lot of times, researchers such as myself will report new malware to Apple, basically saying, hey, there's this new malware, it's signed with this certificate. Apple will revoke that certificate, which is a good thing, which means it won't run on it won't run on macOS systems, new instances. So new infections are basically shut down. But again, we never see any reciprocity where Apple reaches out to the antivirus community or security researchers as myself and say, hey, just to let you know, there's this really interesting malware that we're seeing target Mac users. By the way, we revoked their certificate. Anyways, I'm not going to go on a rant about that, promise, but it would be nice if Apple would be more proactive in sharing some of their research and findings with the external research communities and the antivirus companies. Because again, what the antivirus companies will then do is create signatures for this malware, which will then protect more Mac users and detect existing infections. So Apple revoking the certificate is not going to basically detect or stop existing infections. It's going to prevent new ones, which is a step in the right directions, but it's not going to prevent or detect existing ones. So again, Apple, if you're listening, I would love some more transparent teamwork. Maybe it's something we could get to in 2018. All right, moving on. We can look at the file code for this and basically look at the info.plist file. And again, we can see that this malware is registering these custom URL schemes, specifically something called open URL 262207. So again, this proves kind of the proof of concept we created that abused these custom URL schemes to launch that is the same attack that these attackers were using, which is not too surprising because again, in his talk, Taha mentioned that this is what the attackers were using. So again, we can dump the info.plist file of the malware and we can see that it has some custom URL schemes. Again, this means that when a web page tries to browse through these schemes, it will automatically get launched. So let us now pop over and do a little bit of reverse engineering. Let's see, do I have this loaded in Hopper? Entry point, I do. Okay, so now we have these samples. Again, they are available online. If you go to Objective-C.com and click on malware, and I'll post this link here. This is my malware collection that I share with the world. Very proud of this. When I got into malware analysis, I was always like begging people for samples because people don't really like to share samples, which bothers me. What I try to do is anytime there's a piece of Mac malware that's publicly discussed or available, I try to get a copy of it and post it on here. So if you are doing a Mac malware analysis or you're interested in that, or I tweet about some Mac malware, more than likely the sample is available here. So we can type wind. Oh man, did I lie? I haven't uploaded this yet. No, it's there. I just haven't updated the page. WindTail. If we go to, okay, so I need to update this page, but the sample is here, I promise. It's just not in the search. Objective-C.com/download/malware/windtail.zip. Yep, that downloads that. Yeah, I'm not going to paste that in the Twitch channel because I don't know what the rules are about sharing malware. But I will add that to the search page so it shows up here. But that sample is available, and you can actually probably grab it from the blog as well. Yeah, so if you go to this blog again, you can download the samples for that. Sometimes I just not as the malware collection is not as up to date as I should be. I just don't update the database as much. Okay, so we download the samples. We're going to now open them in a disassembler to kind of briefly look at the capabilities of the malware, figuring out what it does, how it infects the system. So I wish I could make this code bigger. Can I do magnify or something? Does anyone know how to magnify things on Mac OS? It's like a application, locate, magnify pointer. I'm gonna Google this. Mac OS magnify. Use a zoom window in Mac OS. This looks complicated. Okay, well, hope it's at least somewhat readable. Let me just see. Yeah, you can kind of see that. I'll talk through it. So, yeah, Control++ doesn't really do anything. Edit, font, bigger. Oh, come on. Hopper. I have a good idea. We will open this in Notepad, text edit, and then I can zoom into that. All right. So this is the disassembly from the entry point of the application. So what we've done is we've taken the WindTail malware and we've opened it into Hopper. Hopper is a disassembler. There's IDA Pro, there's a variety of others. I like Hopper because it's kind of Mac OS focused. So it does really well, for example, with Objective-C code. It's also, I don't know, like $50 versus IDA, which is, you know, hundreds and hundreds of dollars. So code begins at the entry point, and we can kind of skip through a bunch of this stuff, but we can see that it's going to call this subroutine at address 10001cc4. So in Hopper, we can double click on that. And again, I'll copy and paste this so we can see that into a bigger window. Again, double clicking takes you to that. And we can see that this chunk of code gets the path to the main application, creates a URL from that, a file URL. So this is just getting a path to its own application, and then calls ls shared file list create, and then ls shared file list insert item URL. So if we Google these APIs, these are functions that Apple implements. These are, Mac APIs. Did I spell that wrong? Huh. Apple sometimes doesn't document things very well. Or I'm bad at Googling. Now see, no available, no review available. Thanks, Apple. But this is a well-known API, so we can click about things. So we can basically see that in this, for example, piece of code, there's a comment that says insert an item into a list, adding it as a login item. So if you have studied Mac OS and learned about methods of persistence, one way you can persist an application is via a login item. And when I say persistence, I mean a way to ensure that something is automatically restarted every time the user logs in, which is important if you're a piece of malware, because otherwise, if you don't persist and the user reboots the system, you will basically have lost code execution on that block. So again, persistence is very important. So what the malware here is doing is persisting itself. And we'll execute this in a VM, and we can actually show that that's what's going on. So let's hop over to this VM. Let's close some of these tabs. Let's copy the samples that I downloaded from the interwebs. Okay. Again, if we do, come back here. Keyboard, where did you go? Oh no, this VM die. Ha. Okay, that works. Well, I'll just close this. Oh, there it was. Let's do this again. I'm just going to show that even just copying the malware samples to the VM caused macOS to register the applications to handle these custom URLs that, again, can be triggered via the web to kick off execution of the application. Okay, so we're going to grep for, what was it called, like final presentation or something? grep.i to make it case insensitive. Okay, so you can see there's a path here, and if we just dump the whole thing, pipe it into less so that we can look at the contents of it better, otherwise it will just scroll by, search for that. We can see that, again, the operating system has registered for that, and if we come down here, there should be something about custom URL schemes. We can see the executable is called USR node. That's just the name of the binary in the application. And yeah, we can see that there's this custom URL scheme. Again, this is what the APT attackers use to launch the application from the web. Once again, Safari had automatically downloaded and saved the file. Yeah, and here you can see a claim. This basically says, hey, I'm going to be the URL handler for this specific URL. So if in Safari, we came over here and we executed this, blah. I don't know if this is going to work. It should work. Now, it's going to basically ask us, do we want to open the application? Again, some users would probably click yes. Again, a very powerful exploitation technique. So we're just going to manually run this in a VM. See what happens. Cool. The certificate has been revoked, so I don't know if it's going to actually be allowed to run. We have a pop-up from BlockBlock. BlockBlock is a tool I wrote that will monitor for persistence. Awesome tool. I would recommend installing it. What it has detected is that something has added a login item to the system. Look at the ancestry. We see it's something called background task manager. This is what actually processes the installation of a login item when someone makes that. I heart BlockBlock. Thank you. Me too. So we can basically see that this Apple process has persisted final presentation.application. Let's click allow just to allow the persistence. We can also kick off knock knock, which should show this persistence as well. But now if we come and look at the installed login items, we should see that something has been persisted called final presentation. You can view that via opening the System Preferences application, clicking on Users and Groups, and then Login Items. And sure enough, we can see that there is something. It's funny, there's actually a bug in the malware. Because they persist before they install themselves, they actually end up persisting twice. So kind of a bug. I'm not sure they just didn't test this malware enough. But as we'll see when we go back to the disassembly, actually, we'll look at that right now. Again, before they call the application's main, they persist. So this means this is the first thing they do. So once they have finished persisting by creating a login item, which again, block detected, and knock should probably detect it as well. What knock does is it enumerates persistence location. So if you think you might be infected, you can just run this on your system. And you can see that the final presentation application we ran was indeed persisted as a login item. And we can see, as I mentioned, it was persisted twice. The first thing is we can see the path was the instance I ran on the desktop. And then, as we'll see in the disassembly, they copy themselves to a more hidden persistent location, and then they re-persist. And here's the path for that. So you can see they copy themselves to the user library, the user's library directory. So again, there's a bug. They shouldn't have persisted twice because now they show up twice, and yeah, that's just not, very, very stealthy. But there are bugs in malware. Malware authors are humans too. So yeah, these LS APIs are how you register yourself as a login item. And again, a login item will be automatically executed every time the user logs in. So if you're writing a piece of malware, this is a neat way for you to gain persistence. So once they have persisted, they call NS application main. This will call a method, a delegate method called application did finish launching. So that's just something if you do Mac reverse engineering or read or write Mac apps. But again, if you see the main function, so this is probably main. If you write C code, you're familiar with that. Calling this NS application main means that code will start executing again at application did finish launching. So we can go there, and again, I'll copy and paste this code so we can see that here. And we can see that what it's doing is creating some files and formats. One cool thing about analyzing code that's written in Objective-C is that a lot of the method names are very verbose. So we can see it, for example, allocating a date object, right? NSDateAlloc. We then see it creating a string from that date. So again, very self-explanatory. We then see they build a path using /date.txt. They check if that file exists. Again, we get this all just from reading the methods they call, right? So we know what they're doing. We then see them creating a random number and then writing that to a file. Now, if that write fails, they set a default called generate device name, and they spell that wrong. So what we can probably do is we can go see if we can find this file called date.txt, because it looks like the malware is creating that. So if we come back here, I might have to run the malware again. We can, let's run my process monitor object class. And then we can run a file monitor, fsusage. It's a built-in utility in Mac OS. We run it with the -f file system, and we're going to grep for that date.txt file. This basically says, please record any files that are created called date.txt. So we might have to revert this VM because I already ran that. No, we can see that. Okay, cool. So yeah, we can see it accessing this file called date.txt. So we can see what's in there, if anything. Yeah, cool. So we can see that this is some random number. And if we go back to the disassembly and we look at the error case where they set this key called generate device name, this is probably a unique identifier for the implant. So when you write malware and you infect a lot of systems, it's very important to differentiate between the different types between the different targets, right? Because if you infect 1,000 targets, you have to have some way to differentiate them. So what a lot of Mac malware or malware authors will do is they will generate a unique device ID, and then they will save that or store that somewhere. And that's will then show up on their command and control server, and that's how they can identify that specific instance. So again, the way they generate that is by generating, getting today's date and time, and then combining that with a random number, and then saving that to the file system. Then what they do is they call this to-fel method. So let's hop over and take a look at what that is. Again, in Hopper, we can double click on that. And we can see that that is just invoking some other method called appdele. They call init and then sys. These are probably just arbitrarily named methods. You have to have string-based methods, and this is probably just an obfuscation approach. Instead of saying like connect to command and control server, they don't want to give away what the method does via the name. So we can come over here and we can look for some of those methods. So for example, we can look at the sys method. And yeah, we can also, we can see that calls encrypt file. What was the other one called? AppDelegate init. So we come over to Hopper, we look for that. Okay, this is an interesting method. So again, this is where it gets a little hairy, so we're not going to walk through all of this because who likes to look at disassembly code? But we can see that it's doing something with what looks like a large obfuscated string. And it's passing that to the UP method. So let's pop over and see if we can find the UP method. Okay, looks like it's right here. Again, let's copy that into this. And we can see that this UP method allocates a chunk of data, calls the decode method, and then calls AES decrypt with passphrase. So this is likely decrypting an encrypted string. So what a lot of malware authors will do is they will have embedded strings like this in their code. And this is probably the command and control server or some other sensitive information that they don't want to be easily readable in the clear, right? So they obfuscate it and they encrypt it. Now, they call AES decrypt with passphrase. So if we go back to the Hopper, our disassembler, and look at what that's being called with, we see it's being called with this CF string. It's actually easier if we look at this in just pure assembly mode. This is getting pretty in depth. But here we can see that that method is being called with this. And I'll copy and paste this again so we can see that. So the AES decrypt method, it's called AES decrypt with passcode, is being passed this chunk of data. So what do we think this data is? It is the AES decryption key. So this means we can decrypt this content because they're decrypting it with an AES key. So there's two ways you can do this. You can write your own AES decryption routine, or it's actually easier just to set a breakpoint on these, this decryption routine, let it execute, and then once it's executed, just print out the code. So let's try to do this in a VM. Now, this doesn't always work because for some reason my debugger is kind of messed up, but let's give it a shot. So first I'm going to kill the malware. And what's it called? Final something. Grep. Is it running? Should be two instances. Yep. So there's this one here. So if I kill this, kill that 9, that, and then kill the desktop instance. And then we do a PS again, just to make sure it's gone. Okay, now the malware's not running. So what we're gonna do is we're gonna start it under a debugger. LLDB, what do we call it? WindTail, final presentation.app. Cool. So the goal here is to set a breakpoint on that decryption routine, let that execute, and then dump what it's decrypting, basically having the malware decrypt the code for us. So we need to know where to set a breakpoint. Unfortunately, I don't have a good luck setting decryption breakpoint or breakpoints on, what am I saying? named base method, so I usually try to find an address. So let's first set a breakpoint on the very beginning of the code, the entry point, which is right here. So we can do that with the b command, and we give it the hex address. And then let's set another breakpoint on the main method. Again, a breakpoint just tells the debugger to stop code execution when it hits that code. So I'm just going to set a bunch of breakpoints, and hopefully they all get hit. We're going to set a breakpoint on the main code, and then we're also going to set a breakpoint on that UP method. I think there was there two? Was there one? UP. Okay, we'll set on both because I don't know which one gets called. And hopefully this will work. It's funny, I do a lot of malware analysis, but I still pretty much just wing it every time. Okay, so we set now. Oh, we need to put a OX to tell it a hex address. Okay, I'm just going to take a snapshot of this in case I miss the breakpoint and then the malware starts executing, so we don't have to kill it and rerun. So now we're going to hit R for run. This tells the debugger to start executing the code. You see that it launched that. And yeah, this is annoying. It doesn't hit the breakpoints. Grr. Ha. Not ideal. Let's see. LS failed with application. Interesting. So again, the debugger had some problems. Oh, it's probably because... Okay, let's try this one more time. Let me do a few things. Let me just make sure it's executable first. Desktop, what do we call it? WindTail, final presentation context. I think this one was. Yeah, I was looking at another piece of malware. It didn't have the executable flag set. So maybe we'll have better luck if we specify the full path to the application user node. Will that work? Okay, let's try to set those breakpoints again. Thanks for bearing with me. Like I said, I don't know why, but on that VM, this instance of the debugger sometimes doesn't hit breakpoints, which is frustrating. Very frustrating. It's like, come on, debugger, you had one job. So let's run this. Again, launched. Yeah, and doesn't hit it. So if we Control C this, just make sure to see where this is loaded. See if it's ASLR'd or something. The other thing is, let me make sure I'm opening the same file. Because again, if we don't have the exact addresses, that would be bad. So entry point is at 1C88. Is that what I set the breakpoint on? Yeah. Okay, well, I don't know why these breakpoints aren't hitting. Let me try one more time. What could we try instead? Let me just set it on a random address here and see if that works. BOX, or let me try BRS-A. This is another way to set memory breakpoints. Okay. R restarts it. Again, I'm just trying to get it to break. Okay, that works. All right, so maybe it didn't like my other breakpoints method. So again, we're going to set a breakpoint on the UP method because that is what is doing the string decoding. There's two instances of it. I'm not sure which one gets hit, so we will set them on both. BRS-A OX address, and then again, get the address of the other method. 3645 BRS-A OX, boom. Okay, so now if we hit continue, hopefully that gets called. Cool, so we hit breakpoint. If we do BT, it gives us a backtrace. We can see someone called us. And now if we execute finish, that basically should tell the debugger to execute the function but stop right before it exits. So now in the EAX register should be a decrypted string. Whew, there is. Okay, so there's a few LLDB tricks I just did. The first thing is we set a breakpoint at the beginning of the string decryption function. The goal again is we want the malware to decrypt the strings for us because we're lazy. We don't want to run our own debugger. When we hit that breakpoint, we then typed finish, which is the debugger command again that says, please execute the function, but stop right before you exit. Because at the end of the function, the string will have been decrypted. So when the function is finished, the return variable is going to be in the RAX register. This is just how values are returned from a function. And I just assumed that the string decryption function would return a description ring. Oh, yes, sorry. Can you move this? Better? Yeah, awesome. Okay, so what we did is once the function finished, we basically called PO, which says print object, and we gave it RAX, which again is the RAX register, which is what we assumed holds the value of the decrypted string. So yeah, they decrypted library. Again, that's not super interesting, but again, we can type C to continue, see if we hit that again. Again, when we hit the breakpoint, we type finish. We're then going to print this out again. If you really were going to do this, you can see doc. That's something interesting. Maybe it's looking for doc files. You could create a LLDB command that would automate this, meaning every time that breakpoint was hit, it would then finish and then print out this. So you could just run and decrypt all the strings. But I like to do it manually because it's kind of, I don't know, more interesting. So again, next breakpoint, finish, PORAX, docx. So it's maybe possible that they are looking for documents on a system. Again, if you're going to infect government officials with a custom Mac implant, it's likely that you're probably wanting to get contents of all their documents, PDFs, et cetera, et cetera. So let's just keep running this. Finish, and then keep printing this out. Yeah, PPT files. So again, these are all the strings they're decrypting. PDF. Oops, what is, we need to hit finish one more time. XLS, okay, I'm gonna run this a few more times, see if we get some more interesting stuff. Finish, wonder what else they're looking for. Text files. Again, you can see why you wanna automate this. PPT files, okay. Oh, awesome. This looks like the address of their command and control server. So this is cool. When you're doing malware analysis, usually the 3 or 4 main questions are, how is the malware persisting? We showed it persisted via a login item. We then kind of answered the question, what is this malware doing? It looks like it's looking for documents, or at least has encrypted references to file extensions likely of interest. And then we've now just decrypted what looks like a command and control server, and it looks like this is where the malware is going to connect into for tasking. And again, it looks like it's probably going to pass some parameters. This is probably the ID of the implant, or perhaps some survey information, for example, the type of computer, the list of processes. A lot of times malware will connect in and pass in this information. So if we were running a network sniffer, we'd probably see it try to connect to flux2key.com. We're just going to keep running here. Yeah, and that's the last string it decrypts, because probably once it can't connect, it errors out. So we can see there's an error code here, basically saying NS URL connection finished. And this is probably because that domain is now offline. So if we come back and to grab the CNC server, ping this, yeah, I think if you do an NS lookup, that server can't find, yeah, well, maybe do this without the HTTP, but it's probably going to give us the same error. Yeah, so the server can't be found. So basically this command and control server has now been taken offline, which is not too surprising because once the malware gets out, the attackers usually shut down their command and control servers or change them. All right, so that kind of wraps up our talk today. We chatted for a good hour and a half. Awesome. Just to reiterate everything we talked at the beginning about generic keylogger detection, we showed how we ported the Objective-C code to Swift. We showed how we then implemented that into the open source monitor kit framework. We talked about this new app called Reiki that will be released very shortly. Reiki, where are you? That can do generic keylogger detection, both enumerate the existing ones and then also provide runtime protection, which is kind of cool, right? It'll alert you anytime a new event is created. It has a command line interface, which means if you want to scan, for example, Mac computers, you could deploy this and then run the scan, grab the JSON and ingest that. And what else did I want to say about this? Oh, it's also open source. So you can check out the source code again on GitHub. We then talked about WindShift's. WindShift is that APT. The WindTail rather is the WindShift's Mac implant. And there's more information about this in the blog. So if you want some more information about that, feel free to check that out. Kind of go into all the details of what I just discussed. So we talked about how we discovered this new variants of this on VirusTotal, how Apple had revoked the certificate, but didn't tell anybody. Maybe they weren't allowed to. We talked about how it persisted via this login item, again, a fairly common way for malware to persist. And then we talked about how the malware generated first a unique ID and saved it into that date.txt file. And finally, how we were able to decrypt the strings by setting breakpoints on that method and then dumping things like the command and control servers, which again is very important to know. You can then usually see who registered those servers. If you have network logs, you can see if any computers on that. So that's a wrap. Again, tools like block, and knock are able to generically detect and block this malware with no a priori knowledge. Again, because they are designed to look for things like persistence. They say, I don't care how you got on my system, but if something persists, please let me know. So that's kind of cool because, again, originally a lot of the AV engines did not detect any of the malware. All right, so I don't have anything else going on today. So other than getting Reiki out the door, there's no surf, so I'm not going to bail. But if you have any questions, some Q&A, we can chat for a little bit before we wrap up this chat.